Hello and welcome to the last video in this course of Machine Dynamics 2, and the last video is about the forced vibrations of rotor blades. First of all, I would like to state a few assumptions about the excitation mechanism that leads to forced vibrations, namely it's the flow, so the pressure of the flow, of course, that acts via the surface of the blade with the blade and exerts a pressure force so a surface force on the rotor blade. We will assume that there is no pulsating flow, so therefore there is a stationary exposure of the blade and there is a constant rotational velocity. So therefore, of course, the pressure changes, but it changes periodically with the rotational speed, so with the angle, and the angle repeats itself because the rotational velocity is constant, so that we have a periodic in time, a periodic exposure of the blade to that pressure field, which leads to a periodic force that acts on the surface of the blade. So as a consequence of these assumptions, we will, for the force, introduce a separation that is similar to Bernoulli's separation method. So we will separate the excitation in space and time. For the time part, we will assume that it is periodic with the rotational speed or rotational frequency omega 0. So we can carry out a Fourier expansion on S of t, and this leads to a harmonic excitation with respect to time, to a harmonic excitation due to the superposition principle, if of course the equations that describe these vibrations are linear. I mean, you know, they aren't really linear because we took into account the green strain tensor, but we saw that we are able to, I would say, to linearize these equations by introducing the reaction force in longitudinal direction L of x. So we apply Fourier expansion, and then of course just one remark, which should be clear at the end of that course, that resonance is possible. And if we look at the situation where resonance could occur, well, I introduced here, you can see these straight lines. These are lines, well, of the harmonic excitation and of omega 0. If you increase the rotational speed omega 0, then you will find straight lines, and the slope of these straight lines changes with index n. So you can see that we start here with capital omega 1, capital omega 2, and so on. The higher the n, the stronger the slope of that straight line. And then you can see three other lines that seem to be nearly parallel to omega 0, but if you look at the first two, then you see that they are not really parallel to that axis here. Well, what are these lines? The first two are the bending natural frequencies that we will obtain from our equations of motions. Of course, the first bending frequency. Yeah? The first in each direction. So there is one direction where the bending frequency, the first bending frequency, is much lower than in the other directions. Think of a knife. You have one direction where the knife is very flexible. You have another direction of bending where the knife is not very flexible, and this leads to a much lower, in the one case, natural frequency than in the opposite case. And finally, there is really a straight line, and this is the torsion natural frequency. So the natural frequency for the torsional mode that we did not consider and that we will not consider much in the following. Well, what can be said now about this diagram? Well, if we look at points where the natural frequencies and one of these frequencies belonging to the harmonic excitation intersect, then you will find possible resonances. So these resonances that are possible, that lead to, of course, to an increase in amplitude, but not always to a dangerous situations if they are well damped. And you can see that there are many situations where you can find resonances. So you cannot avoid all of these resonances. You can avoid, because these are also only the first three natural frequencies. There are much more natural frequencies. There are much more excitation straight lines. So you cannot avoid all these natural frequencies. What you should avoid are the first natural frequencies. And you can see here an interval for the operating speed of that rotor, which would be possible, which would be, well, beyond that resonance with respect to the first harmonic excitation and below the resonance of the second bending natural, or of the bending natural frequency in the other direction with respect to the second excitation frequency. So there are these ranges in which you can operate, of course, your rotor, otherwise it wouldn't work at all. But also in these regions there is resonance, so there are some amplitudes and some modes that are magnified and other modes that are rather suppressed. And now the question is to design the blade, that is to make sure that you have a safe design with respect to fatigue of that blade, and of course with respect to rupture. And well, this has to take these situations into account, that there might be resonance with respect to some higher harmonic perhaps. And well, we will also look at the static case, at the static excitation here, and then of course at the harmonic excitation, and take resonance into account. That's a little bit what we have to do. What would be the stress that we have to take into account? We have a normal stress due to the centrifugal force. That normal stress is rather time independent. If you remember from the last video what we did in the axial direction, then we took a quasi-static approximation into account. So here is the static contribution. Then we have normal stresses. Our two normal stresses in the two, from the two contributions, from the two directions, due to oblique bending, which is in German schiefe Biegung, and we have a shear stress due to torsion. Well, as I said, the most dangerous case is the bending with respect to the, well, of the knife to the flat side. So, or if you take, instead of a knife, if you take your hand, this would be the flat side, and this would be bending around the flat, or with respect to the flat side, and that would be the most dangerous case, because the blade, as the knife, is very flexible in that direction. So for bending, we need the maximum bending stress, and that occurs at the outer fiber and is given by the following formula. You have, which you know from engineering mechanics 2, you have the bending torque divided by the second moment of area, and E is the distance of well, the outer fiber distance from the geometric center. And for the bending torque, you can insert the bending stiffness, E times I, multiplied with the second derivative of what is called the bending line or the bending deflection, W. And you have then minus EX. You see that the two I's, the second moment of area, cancels here. You have Young's modulus multiplied by the second derivative of the displacements with respect to X. So the task is for bending to compute this second derivative, and this is the solution of the equations of motion. However, now the equations of motion for forced vibrations. So we need to compute the solution, the second derivative of the solution for forced vibrations. So then let's have a look at the equation of motion. Well, the equation of motion is the simplified equation you saw in the last video that it is decoupled from the other bending direction. So the two principal bending directions are decoupled by neglecting all the coupling terms. Then it includes the linearization by introduction of L of x, the force, reaction force in axial direction here. And on the right-hand side, that's the only point where something changed with respect to the previous video, is now the forcing function Q of x and t. In that forcing function, we will take into account not only the excitation, but also some damping, because some damping will be present in the system. And well, that's necessary in order to avoid that the amplitudes at resonance are infinitely high. So what we assume for Q is a damping, which is velocity proportional with a coefficient of beta. It appears with a negative sign because then it would have a positive sign on the opposite side, where it usually has a positive sign. So a damping effect. One could say also it's a negative force with respect to excitation because it tries to exert or to transfer energy from the system into some other kind of energy. And then we have the, I would say, the true excitation coming from the pulsating flow, from the fluid flow. Well, if we insert Q here into the equation of motion and then of course put the damping term on the left-hand side, we arrive at, well, nearly the final version of that differential equation. So this would be our differential equation that we have to solve. And well, I guess you would also say, well, I'm unable to solve that equation. I could use here Bernoulli separation, but I have a serious problem here with that function L of x, for example, that is dependent on x, and I have to take the derivative. So it looks very complicated. So therefore, in this video, I will propose to use a numerical approximation. So let's approximate the solution. How could we approximate the solution? And that's something that is very typical for dynamics. We have a very good approximation functions at hand. Namely, we know the mode shapes. That is, we know the modes, the natural frequencies, and also the mode shapes. And these mode shapes, they satisfy certain orthogonality relationships, as we saw, and they are perfect base for expanding the solution W. So we approximate our solution by an expansion on the eigenfunction base. The approximation would be perfect if n tends to infinity, so we hope to get at least convergence in that case. But as we cannot provide so many terms, as we have to cut our expansion at a certain term, so we have to cut the sum here, we take only the first n eigenfunctions into account, so therefore it's an approximation denoted by a tilde here on the left-hand side. So we cannot hope to satisfy that equation exactly anymore. And these are the functions that are given, the functions with respect to space, the eigenfunctions of the problem that has to be computed beforehand by some approximation method, based on Rayleigh quotient, or there are some other methods that I will present in my course on computational dynamics. And these are the functions that we are looking for, but theta g. As they are only time dependent, we will arrive at ordinary differential equations for these functions theta j of t. Well, if these are classical linear ordinary differential equations, there is a high chance that we are able to solve them analytically if they decouple. Well, if not, we are able to solve them numerically by some numerical integration scheme. So this is the idea. The question is, how do we produce these ordinary differential equations that describe these theta j? For this, we need an approximation scheme. The approximation of the solution, so the setting, the ansatz, is just the first step of an approximation scheme. The second step is, well, we need a rationale, so a logical way to produce such ordinary differential equations. And there are many ways to do this, and I would like to present you here one. The first thing is I would like to compute the approximation error and then try to minimize the approximation error in a certain sense, of course. And what this means will be shown, well, in a few minutes. So first of all, how can we specify the approximation error? Well, on the left-hand side, there is something that will be affected by introducing that approximation here. On the right-hand side, there is something that always takes the same value. You can do anything here as an approximation. The right-hand side will always be P of x S of t. It's the excitation, so it's independent of the solution. Therefore, it's on the right-hand side, right? So if we take the difference between what we have on the left-hand side and on the right-hand side, the difference will be 0 if we found the exact solution. However, if we have only an approximate solution, the difference between the left-hand side and the right-hand side will not be 0, but will be an error field, depending on space and time. And that's the approximation error. So you take the terms on the left-hand side, you took the term on the right-hand side, you throw it on the left-hand side. That way, the equation has been obtained. The other way will be possible, of course, as well. And the difference would be the approximation error, the difference between left-hand side and the right-hand side. And that difference is space and time dependent. So strictly speaking, epsilon is a function of space and time. So what we would like to have, of course, is still the time dependence, but not the space dependence, because for the space dependence, we set here already our eigenfunctions. So these functions are given, pre-computed. So how can we reduce that equation to a completely time-dependent equation? Well, if we project the space dependence on some functional space, and then we require that the approximation error that is projected, the projected approximation error on that functional space, is equal to 0. That is, we strive to reduce the approximation error to 0 in a certain subspace, hoping that this subspace is large enough to produce a good approximation of the solution. So the question is which subspace to choose. Then that satisfies this condition. And with that approach, we try to get a good approximation. So what could be a good function space to project that error on? Well, that function space is described, of course, also by a base. It's a vector space of functions. So it would also have a dimension that is infinite, so you not countably infinitely many functions. You could, for example, take harmonic functions or polynomials or whatever. But if you think of what you did here in dynamics, then why shouldn't I recycle these eigenfunctions again and use them also for the projection on the functional space as the base vectors of the projection space? That seems to be very clever, right? Because there are orthogonality relationships between these eigenfunctions. And if I project again on these eigenfunctions, there is a certain hope that I will profit from these orthogonality relationships once again and reduce the problem to nice ordinary differential equations. So that's the idea, to be very efficient. So that approach is called a Galerkin approach. So what we do is we take that approximation error to the next slide. Here it sits, and we project it on that function space that is spanned by our base vector, and these base vectors are again the eigenfunctions, so the mode shapes. Again, n mode shapes. And this leads then to ordinary differential equations for the expansion coefficients theta k of t. And the advantage of this approach is, as you will see in a few moments, that these ordinary differential equations then decouple because we have that orthogonality relationship, and the decoupled ordinary differential equations, well, they are second order linear ordinary differential equations. So if they are decoupled, they represent single degree of freedom oscillators. So these ordinary differential equations, these decoupled ordinary differential equations, are easily solvable even analytically. So let me recall these orthogonality relationships. We have two of them. The first one is with respect to the mode shapes, if they are multiplied by mu. If mu is a constant, you can take it out of integration. And the second one is now enlarged. Before we saw it's the bending stiffness that is multiplied by the second derivative. And now, as we also have that term L of x, and if you remember the derivation of the Rayleigh quotient for that enlarged system, you will see that there is a relationship, a second orthogonality relationship that has to take that L of x into account, and it works here with the first derivative of these mode shapes, capital W. Okay, so let's apply this. Let's first insert the approximation into our Galerkin condition. That is, we have here our WK on which we project. We put again the excitation on the right hand side, and we inserted for the approximate solution the expansion here, which is a series running sum running from 1 to n. The second derivative with respect to time, mu, first derivative with respect to time, and here we have, well, the bending stiffness contribution and the contribution from the centrifugal force or the reaction force L of x. Well, now let's carry out partial integration in order to shift the two derivatives to that w and that derivative here to the other w, in order to be able to apply the orthogonality relationships to that term as well. Because this term is already perfect. If mu is a constant, then you can also apply the orthogonality relationship for the second term, because it then holds for the two functions w, and mu would be a constant that can be taken out of the integration. So for this contribution here, for this term, we have to apply partial integration, and after that partial integration we will see that the equations decouple. So a partial integration is classical. So for the first term we have to do it twice, so we arrive at the positive term. The two derivatives are shifted to wk. However, we have to take our boundary conditions into account in order to make sure that these terms, the boundary terms, disappear, vanish. So for the first one, we see that at the free end, the third derivative is equal to 0, and at the clamped end, so at x equal to 0, wk is equal to 0. For the second part, we see that also the first derivative is equal to 0 for x equal to 0, and the second derivative will vanish for x equal to L. And for the other term, we will see that, well, also L vanishes for x equal to L. The centrifugal force is 0, and we have, or the reaction force is 0, and we have, due to the clamped end, we have wk equal to 0, also wj prime equal to 0 for x equal to 0. So indeed all the boundary terms will disappear. So therefore we can shift the two primes to wk, and here the prime to wk. So this is done on the next slide, where also the orthogonality relationships have been applied, assuming here that mu is a constant, so that we can also apply the orthogonality relationships to the second term. Well, can we further simplify that equation? I mean, that looks also good. You have to compute all these integrals, of course, in order to get the coefficients in these decoupled ordinary differential equations. But if you look at the quantities that they describe, namely the theta k, these decoupled equations for k running from 1 to n, then you see that that equation looks already very nicely, namely that it's a classical single degree of freedom oscillator, just the variable is denoted by theta k instead of what has been before an x or y or something like that. However, for the coefficients, one would have to compute, as I said, one would have to pre-compute by some approximation scheme the eigenfunctions, and then from that integration of the eigenfunctions you would get the appropriate coefficients. But one can further simplify that equation by introducing the Rayleigh quotient here and the natural frequency, because the natural frequency must be known. If you know the mode shapes, then you usually do not only know the mode shapes but also the complete mode, so the natural frequency and the mode shape. Yeah? So we introduce the Rayleigh quotient here. So this allows us to simplify the second term and to introduce here also the integral from 0 to L on mu omega k squared. So then let's divide by this. So let's somehow standardize that equation so that the highest derivative stands in a single term in the first term. So let's divide by that integral running from 0 to L mu wk squared dx. Then it appears in the denominator of the damping term. And that damping term can now be written as 2 dk omega k. And for the Rayleigh quotient of the kth mode, we introduce the natural frequency omega k squared. So this term then is quite simple. And on the right-hand side, we would have to compute that ratio of that given function p of x, the spatial distribution of the pressure field, divided by the integral on mu wk squared. Yeah, and this would be our ordinary differential equation. And now with these abbreviations and of course all these pre-computations that have to be done, it looks really quite simple. Now let's analyze that. So let's see how the particular solution looks like and how that equation helps us to design our rotor blade against fatigue. So here again is that equation, one of the equations of motion that are decoupled, namely for mode number k. We are looking for the particular solution only because there's damping, and we know that the homogeneous solution then decays exponentially fast. There's light damping usually, as we have a nice lightweight structure here and very energy efficient, by the way. So I would like to consider two cases. The first one is the static load, and the second one is then a dynamic load or resonance load, for example. So let's look at the static load, where S of t is then equal to 1 and where we have some space-dependent function. Now, as there's no time dependence on the right-hand side, due to that 1 here, on the left-hand side, a static solution is really sufficient. So we get a theta k 0, which is then equal to that epsilon k for that very special case where we plug in p naught instead of p here and divide by omega k squared. So it would be epsilon k divided by omega k squared, and for that epsilon k, in order to evaluate it, you have to plug in p naught instead of p. So nice. Seems to depend on not much, right? On the pressure distribution, P naught, on the mode shapes, and on u and on omega k. But if you have a further look, then that mode, omega k and wk, well, depends on, for example, the bending stiffness, could depend on the rotational speed also, as we saw that the rotational speed influences the modes, the natural frequencies, depends of course on mu and also on L. Not only by this term here, but also via other mode omega k and wk. So all the parameters are present, also they are not so visible in that expression here. Okay, this would be the static part. Now let's come to the harmonic load, and let's consider just a certain capital omega here. The classical setting would be to put a magnification factor and a harmonic function similar to the excitation, so cosine harmonic, but with a phase shift because damping is present in the system. You know then from Engineering Mechanics 4 how to compute by comparison of coefficients of the sine and cosine harmonic terms in capital omega t, the magnification factor, the magnitude or amplitude Vk, and also the phase shift tangent of phi k. The formulations are given here, and also here you see that you have to pre-compute all these coefficients and that the solutions here depend on the system parameters of that blade, as seen before for the static case. Now let's have a look at resonance. What happens if we have a resonance at capital omega is equal to sum of these omega k's? So it happens that for some value of k, omega k is equal to capital omega. So then we call that resonance magnitude, which is then just epsilon k divided by 2 dk omega k squared, because the first parenthesis then will disappear. And you know that for resonance, a phase shift is just pi divided by 2. So that instead of a cosine function, you would arrive at a sine function of omega kt, because omega k is equal to capital omega. So this would be the excitation, but as a sine function due to that phase shift. And you would have the amplitude epsilon k divided by 2 dk omega k squared. Well, and this would be a maximum because this term then is equal to 0. So the complete particular solution in that case is a superposition of all harmonics. However, there's one harmonic that stands out, namely that resonance here. So we can simplify, we'll do that later on, simplify that particular solution by taking only the resonance term into account and neglecting all the other terms. So let's look at the consequences for the stresses. As we want to design our blade, we have to compute the stresses and then do a fatigue analysis. Well, for the static load. For the static load, the bending stress is given by just taking theta 0k into account. So no time dependence here, but in that formulation, all the modes running from 1 to n would be present. However, in practice, only the first mode is that one that leads to the highest stress, bending stress, with a certain remark that due to the mode shape, if you consider a local stress, so local with respect to that value of x, there could be also some other mode that is dominant. So you have always to look also at the maximum of the second derivative. But usually it will be that first mode that should be taken into account. Now, if we look at the harmonic load, then also we have a superposition of all the modes, because this was the setting, the ansatz for the approximation, for the approximate solution of our partial differential equation at the very beginning that described forced vibrations here. So we have to take all these modes into account and their contributions via the analytical solution given by a magnification factor and the phase shift. And as I said here at that point, well, we will look at the resonance with respect to the natural frequencies. So there is that resonance part, and then there are all the other contribution in that sum except this resonance part. And all the other parts will be negligible, will be very, very small, and on this part will have an amplitude that is much larger than 1. So therefore we neglect all the other contributions and take only that resonance contribution into account here. So in fact, so what you have to do is, for the harmonic load, you have to compute epsilon r, and it's the epsilon r and the dr for just one case. Of course, you have to know where the resonance occurs, so you have to compute all the mode shapes beforehand and then evaluate epsilon r and capital Dr just for one mode shape, namely for the resonance mode shape. And similar for the static load, there is just one case that you have to evaluate, and usually this is the first natural frequency that you have to take into account there, or the first mode that you take into account. So basically, all these computations in that Galerkin scheme have to be done only, I would say, for 2 modes, for the resonance mode and for the first mode. And that's it. So this really reduces the computational effort to the determination, of course, of the modes, and the rest is a simple post-processing step, I would call it. Okay. Is there something else? Well, this was for the bending stress. We also have the longitudinal stress due to the centrifugal force, but that can be easily taken into account. It's just L of x, where we did a static, quasi-static approximation divided by A of x. But don't forget it. So we have longitudinal stress, so normal stress due to centrifugal force, and normal stress due to bending. And so therefore I will come to the conclusions. You need only W1 and WR. Well, of course, you have to know the resonance natural frequency. So I guess you would have to determine at least all the natural frequencies until you get the resonance natural frequency. For the mode shapes, of course, you could skip and just compute the first one and the mode shape for resonance, which is denoted by index R here. For the damping, of course, damping is never very good known. So the fatigue stress is uncertain with respect to damping. You take, I would say, a safe approximation of the damping into account in your system. But the damping also in measurements, the damping changes very heavily and affects the result, and this leads to a certain uncertainty. Certain uncertainty is quite well to an uncertainty in the fatigue stress, and there are safety factors also to take this situation into account. And for the fundamental resonance, the maximum stress is at the fixed end. And this is the situation where you usually find the maximum stress. So if it comes to the axial position of the maximum stress, then it's usually at the fixed end, but not always. The boundary conditions could be different. So there could be some flexibility and not a fixed end. And of course, there could be some other modes that are in resonance, or higher modes that are in resonance, and then it's not sure that the maximum stress really occurs at the fixed end. So for higher resonances, and especially for tape plates, the stress maxima can be at other locations, and there is one other location that is very sensitive also, not only to stress, it's the tip, but also to uncertainties, namely also to geometric uncertainties in that structure, because what we assumed here is a rotor that is perfectly symmetric in order to have that stationary field. And in practice, this is not the case. So what you will find in practice is that there are disturbances of that perfect symmetry of your rotor with respect to the structure of these blades. And this leads, so you have global modes of the whole structure. So considering the rotor and all the blades as one structure. So think of a finite element approximation you would do of that whole structure. And what you would then see if you introduce slight disturbances of the geometry, of the symmetry of that structure, then you will find a concentration of some modes and mode shapes, so therefore also the amplitudes, on certain blades, and especially on the tips, also on the tip forces on these blades. And this leads also to safety factors that have to be taken into account when designing these blades. And well, these safety factors, one tries to reduce them. We also had some nice research projects on this at my institute, because, well, you want to have a lightweight construction and a very efficient construction. And if you have to introduce high safety factors due of these symmetry breakings, disturbances of the symmetry, then, well, you cannot be very efficient. So you have to try to reduce them as much by doing very, very good simulations that take possible disturbances that represent classical manufacturing disturbances and disturbances or uncertainties in the geometry coming also from operation into account, trying to classify where higher loads might occur, and this allows you, such a detailed analysis allows you then to reduce the safety factors. Well, what else do we see? Well, as I said, the modes might change depending on the boundary conditions. The computational procedure is the same, but that could lead to maximum stresses that occur at other positions than by taking very simplified boundary conditions into account, as we did here in our analysis. So, and if, for example, if there are elastic restraints, then they always reduce the stress. Well, and that's all I would like to tell you already about the forced vibrations. So what you saw is a nice scheme, the Galerkin scheme. That's not only applied here for these blades, but the hidden story is that this is a typical numerical approximation scheme to transfer partial differential equations into ordinary differential equations to make use of, well, what you have obtained from the homogeneous solution, namely a nice set of mode shapes that is problem specific. So you have a problem specific approximation. If it happens that the homogeneous problem is too difficult to solve because of some nonlinearities or something else, you could try to reduce it to a simpler system. Of course, that must be realistic, that is solvable, and try to use these approximations of the mode shapes, or approximate first the mode shapes, the homogeneous solution, on that basis, and then uses these approximations again in the Galerkin scheme for the forced vibrations. So this general procedure is not only applicable to blade vibrations, but to many, many other problems in dynamics involving structures, like these one-dimensional structures, the rotor that we saw, but also, for example, two-dimensional structures as well. Yes, and well, with this, I would say, nice outlook to typical applications in dynamics, I would like to close not only this chapter, but the whole course on machine dynamics 2. I wish you all the best for your exam. And if you have any questions in the preparation of the exams or regarding these videos, or if you have any suggestions, any comments, do not hesitate to contact me. My email address is just my last name, Proppe, P-R-O-P-P-E, and then KIT.edu, and there are no stupid questions, really. So, thank you very much for your attention and all the best to you for the exam and for your future, of course.